All right. This one is more difficult because we have a weak base reacting with water according to this reaction. So instead of dealing with Ka, we're dealing with Kb cubed, right? So it says write the equilibrium constant expression Kb for the reaction represented above. Just to take a second, what's happening to this as it goes to here? It's acting as an acceptor or a base. That means that this is the conjugate acid, this is the base, and water here is acting as an acid and becoming a base. So I'm just going to put A up here. I'm going to switch to a better pen. So who goes on top? Products. They had to pick something big and huge. She has to go through every one of those drawers. Can you hear it? There's a lot of them. And who goes on bottom? So here's the thing you guys have to consider. Is that right there is going to be worth some points, right? Even though some of this other stuff takes like 3 to 4 minutes, that right there, we should all be able to sit there and say, oh, these things go on top, these things go on bottom. I get points. A sample of aniline is dissolved in water to produce that many milliliters of that solution. The pH of the solution is this. Calculate the equilibrium constant. A sample of aniline is dissolved in water to produce a 0.10 molar solution. This is what they like to do. Aniline is actually the weak what? Weak base. So right there, we know that that is this. The pH is this. So what can we find to get this from the pH? It's the POH. And then we take 10 to the negative of the POH, we get this. Well, for every one of these that is produced, we get one of these, because it's a what? A 1-to-1. Yes? So the KB equals 0.10, right? B 0.10. And then we're going to go ahead and take 14 minus 8.82. 14 minus 8.82. That is 5.18. That is equal to the POH. And then what do we need to do to get the hydroxide ion concentration? 10 to the negative. .607 times 10 to the negative 6th. I'll go ahead and put it here. And that is the concentration of the hydroxide ion and whatever this conjugate acid is. So what can I do to that? Are we okay with me doing this instead of rewriting it twice? Yeah? So everybody understand why if I make one of these, I make one of these. So if I make 6.0607 times 10 to the negative 6 of these, I make the same amount as the other one, right? So now we can plug that into the calculator and find KB. You could, but that's exactly what I'm doing.
Oh, I can see.
You mean the cub Yeah. But where's the remember, it's the hydroxide ion concentration is equal to that. That's easier if you have the KB, right? Because we don't have the KB. Now we have the KB. KB equals 4.37 times 10 to the negative 10th. Right? The solution prepared in part B is titrated with 0.10 molar HCl. Calculate the pH of the solution when 5 milliliters of the acid has been titrated. So for this, we're going to go ahead and do a BCA table. And what do I need to do if it's a BCA table? We need to have the what instead of the moles. Right. Since we're not, if we were at equilibrium here, I could use MOV, right? I'm sorry, here. But we only have 5 milliliters of 0.10. 0.005 times 0.1. Oh, why did I write H2O there? We're adding what? HCl. So we're not getting OH either, we're getting what? Cl minus. What's the Cl minus going to be? In reality, the Cl minus is going to be louder? Spectator ion, right? So we have 0.005 and 0.025 times 0.1, 0.0025. Which one of these are we running out of first? The HCl. How much of this do we get? We have 0, so we get 0.005. And they want the pH of this. Well, guess what? Yeah. This is moles. I took the milliliters and multiplied it by this and divided it by 1,000. With me? Yep. I know that POH equals the PKB plus the log of the moles of the HB, I believe, and the B. So the PKB, I've already solved for the KB. This is the moles of the base. This is the moles of the conjugate acid. A smaller number on top and a bigger number on bottom will do what to this? If we take the log of it, it will make it a negative, right? Take the negative, right? Where's Aiden when we need him, right? We can just test it. So, this is my HB. This is my B. So I'm just going to take 0.0005 divided by 0.002. We get that fraction. If we take the log of that fraction, yeah, we get a negative. So now I'm going to take the KB I solved for up here. I'm going to take the negative log of that because that gives us the PKB. 4.37 times 10 to the negative 10th. And I'm going to use this amazing function where I come up here and I add that to that thing. That gives me 8.757. But that's equal to my POH. Why is that my POH? Because I'm using the PKB and we're talking about the base. So how do I get the pH from that? We take what minus it? 14. 14 minus that answer gives us 5.24. That's what they asked us for. Questions there? Yeah. I got to take the negative log of it first. Okay. Yep. Because this is PKB. Calculate the pH at the equivalence point of the titration in part C. If we redo this, we will see we get how much of the conjugate acid. If we put 0.0025 here, these will cancel out, and we will get how much of the conjugate acid? 0.0025, yes? At the equivalence point, these two have to be what? Equal. And if these are equal, we have minus 0.0025 on this side. We will put plus 0.0025 on this side, yes? So that means that we end up with, at part D, the equivalence point, we would end up with 0.0025 moles of C6H5NH3. Because we're reaching the equivalence point. This is another question. And to reach the equivalence point, we have to give H's to this until it's completely canceled. Right? So how many H's, how many moles of H's do we have to give? 0.0025. So we would subtract 0.0025 from both of these. Would it be easier if I just rewrite the BAC? Okay. And then that would be plus 0.0025 here. Now the problem is that this is in moles. Right? This is moles of the conjugate what? Conjugate acid. Right? So that's moles of the conjugate acid. Well, keep in mind, both of these are the same concentration, yes? 0.1 molar, 0.1 molar. So how many milliliters of this HCl are we going to have to add to cancel that out? The same volume. Why? Again, because it's a 1-to-1. And what is 25 plus 25? 0.050 liters. Where am I getting the 0.05? This? Because we are calculating the pH at the equivalence point. And how do we reach equivalence point? Yeah, I think I just need to write it for you guys. So if we take a look, the same BCA table, right? How many moles of this do we have? Yeah, right, because this is this. What's the only way we can cancel out this many of that? By adding 0.0025 of this, right? Because that's equivalence. So which one of these is going to run out first? They're the same, right? So we're going to minus 0.0025, minus 0.0025, but on this side, what are we doing? We have 0, so we're going to add 0.0025. So after, we have 0, 0, and 0.0025, right? But how many milliliters of this did we have to add? Well, if it's 0.10 molar, just like this, we had to add 25 milliliters of both of these, right? So what does that mean? Well, that means we have 0.050 liters of solution now. 0.0025 divided by 0.05. That gives us 0.05 molar solution of this. But this is the conjugate what? Acid. We want to find the pH, right? Well, we know that the Ka equals the H plus and the A minus over the concentration or the Ma of the conjugate acid. And what do we know about these two? They are what? They are the same. We don't have the Ka, but we do have the what? Kb. How do we change the Kb to the Ka? 1 times what? Right. Somebody's going for student of the month, huh? Nice. So I need to come up here, and I need to take this 4.37 times 10 to the negative 10th, and I need to divide 1 times 10 to the negative 14th by that. That is now my what? That's my Ka. And my concentration of this is what? 0.05. It's on the bottom here, so what do we need to do to both sides? Multiply by 0.05. And this is equal to what? X what? Squared, right? So we have to take the square root of that. And we get 0.00169 times 0.00. I'm going to put this on the camera real quick. Um, 1 times 10 to the negative 14th divided by Kb equals the Ka. And I get 0.001067. This is the hydrogen ion concentration. How do I find the pH from that? Because that's all they wanted from this is the pH. What do? Negative log. I get 2.97. Yeah? That 2.97 is when? At equivalence, yes? Why is this lower than 7? For a strong acid and a strong base, our pH at equivalence is what? 7. We are titrating a weak base, which is going to become a conjugate acid. So that's going to be bring the pH lower than what? 7, right? So if that's going to be our equivalence point, and we want to determine an indicator that will show that, we need an indicator that has a pKa close to that point. Right? So what do we see here? Which indicator would we use? Erythrocin? Erythrocin? Because it has a pKa of 3. That is closest to 2.97. Is that what those signs mean? Or have I been using them wrong the whole time? Is about equal to?
Yeah, that's right.
Now, think about that. You know, it's 9 o'clock in the morning and Mr. Hodson hands you the AP test. Out of that question, how many points are you going to get from it? This is one of the harder questions that could be on there, yeah? This is a lot. I'm not going to lie to you. It's a lot. Where could you pick up?
So I think it's D. Like if you get like 9 point something and so you pick through the failing.
If you sit there and you do that and then you say the other one, the grader should give you the credit. If you get 9 and you say the pKa of this is closest to 9, they should give you the credit. Yep. From everything I've heard from the AP conferences I've been to. If you make a mistake in the math up here, it's supposed to carry through. Next. I got something similar. Yeah.
He stole it from me.
For justification, is all we need is that the pKa is closest to the pH determined. Not the justification. That's all we need. Okay.
Should be. Or maybe we'll use the word erythrocin's pKa is closest to the pH, the change at equivalence, and then say an indicator with that is a good indicator for that situation. But yeah.
Wait, so if you have the Kb and the Ka, you do 1 times 10 to the negative 14 divided by Kb.
Mm-hmm. Yeah. In the week with the laboratory, should we? Those of you that are really good at turning this in, this is going to be easy for you. Those of you that are not so good at turning this in, it's just for kind of.
I actually just did it.
As I said, grades don't matter. The only one that really matters for you is probably the N one. But you juniors should probably care a little bit more than you seniors. Yeah.
I've actually been studying for KP units.
I'm just saying AP. Still short, but it's
What are you doing tomorrow from H? Do you have somebody Zoom with you?
No, I have like 2 classes.
Should we have that up? Are you going to be in a car? Can you Zoom with somebody? Like, oh yeah, put the indicator in there.
I'm excited to see it.
Do you think somebody would be willing to, whoever your lab partner is, would be willing to record it? Oh, she said she might take off tomorrow too. Yeah, just for first period. Weird, right? Very weird.
You can find music for the entire time.
What's that?
Just doing the music, the announcements music the entire time.
Oh yeah. All right. So we've been preparing for this moment for quite some time. There's some pre-lab questions for you here. I'm going to give you an unknown powdered acid. If there's one, we'll change this to 1 gram instead. A particular acid just doesn't work well. If I tell you to change this to 1 gram, that may be needed to do. You need to make sure you know the mass of the unknown solid precisely. You need to dissolve the acid in exactly 100 milliliters of solution. Why is that important? Because that will allow us to get the molarity, yes? Yes. Make sure that I have some standardized in AOH already. And here's some notes. Make sure that you measure out exactly 100 milliliters. This matters when you're recalculating the exact concentration. Mass out the acids on analytical balances. We've got those, so we're good. All of our balances are analytical balances in here, going out 3 decimal places.
If we add the powder in, won't it change the volume by a little bit? Or
I don't think a small amount will matter.
it's like
But yeah.
1 gram won't be that much, right?
Right. So, but that would be a case of error, right? Clean, rinse, fill a burette with the standardized solution. Remember, do a flush of the burette. That's an important step if you're mentioning any lab work on that. Add 5 to 6 drops of phenolphthalein indicator to your unknown solution. Why are we using phenolphthalein? Because we said that all of the things we are using are weak acids. Phenolphthalein changes around 8. Titrate your unknown solution using your standardized sodium hydroxide. 1 milliliter increments, obtaining the pH each time. This graph is the most important thing for this. So we need the pH meters working. This graph is going to be the most important thing for this. Here we have what? If we start with our acid, this is where the acid equals the conjugate base, right? This would be the equivalence point, right? So that means here the acid would be, how do you do that? We would have here, we would have 3/4 HA and 1/4 A minus, right? And here we would have what? Here we have half and half, so they're equal to each other. But here we would have what? Yeah, 1/4 the acid. Remember, the acid's the one with the H on it, and 3/4 of the A minus. So basically, we're making these proportions at these levels. If we know those different amounts, then we can find the Ka. And if we can find the Ka, we can figure out the acid.
What are those lines marking the volume of each?
Yeah. So this one is the equivalence point. So half the volume, you would have the point where these two are equal to each other, right? 1/4 of the volume, then we would have 3/4 the acid and 1/4 of the conjugate base, right? The key thing is we're doing a titration. We're making a great graph, and once we have the graph, we can get the rest of the information. So be prepared to make a titration graph tomorrow. I'll put something on Canvas where it has the updated thing that Jackson made, I believe, right? Isn't that the best currently?
Sure.
The titration graph?
Well, the titration graph, you can just use yours.
Oh, okay.
He made that was for a different lab.
That was for a different lab? Okay. Titration curves, mine. All right, cool. Hattie, I recorded this. I'm going to put an announcement. Yep.